Welcome to the CAV 2020 tutorial. The topic of this tutorial is quantifying information leakage using model counting, given by Tevfik Bultan. My name is Chao Wang. I'm from the University of Southern California, and I will be the session chair. During this session, you can use Slack channel to ask questions. But before the session starts, I'd like to take a moment to introduce our speaker. Tevfik Bultan is a professor and chair of the computer science department at UC Santa Barbara. His research interests are in software verification, program analysis, software engineering, and computer security. His research has won many awards, including several ACM Distinguished Paper Awards. He's also an excellent mentor for students. He received the UC Santa Barbara Academic Senate's Outstanding Graduate Mentor Award. He also took on many leadership roles in the community by chairing conferences such as FSE, ASE, and ICSE. He was also the general chair of ISTA, the associated editor for IEEE TSE and ACM TOSUM. In 2016, he was recognized as the ACM Distinguished Scientist. So without further ado, let's welcome Tevfik and get started.
Hi, everyone. Thanks, Chao, for the introduction. Let me share my screen to start the presentation. I hope you can see my screen and can hear me. So I'm going to talk about quantifying information leakage and using model counting. So I gotta tell you, I get nervous whenever I give a presentation at CAV still, because I remember when I was a PhD student long time ago, giving a talk at Haifa at CAV, and Ed Clark was sitting in the front row, and I was very stressed. so I still remember those days. So that was, there may be people here listening who may not have been born at that time, but anyway, so that was a long time ago. So I'm really very happy to give this tutorial. Thanks for the invitation, Chao. I want to say that I'm going to talk about a bunch of things, and this is all joint work with my current and former students, plus Corina Passaranu, who is, but all the other names I list here are from verification lab, my research lab, but Corina Passaranu is the person actually who actually introduced me to this topic that I'm going to talk about. So I thank her for that. But a lot of my students, and I would just want to read their names: Lucas Bank, Tegan Brennan, William Ayers, Shimanta Saha, Ismet Murat Kadron, Nicholas Rosner, my postdoc, Nestan Siskaritze, another postdoc of mine, Abdulbaki Aydin, Muat Alcala, Fang Yu, Konstantinos Barcis, contributed to things that I'm going to talk about today. So I thank them. I want to do the public service announcement. We are not able to, I was looking forward to meeting everybody in LA, attending CAV. We are not able to do that. I hope everybody is safe and healthy. And, they wear face coverings and wash their hands and stay socially distance, keep their distance. So I hope you're all healthy. Now, I want to do one advertisement here. I'm actually in my office today. If you see my cursor, I'm just right here at UCSB campus. I wanted to come to the office to make sure that the connection is good. I hope it is good. So I also want to say that my lab is there, and I just want to do this advertisement. I'm looking for postdocs and PhD students to work on the topics that I'm going to talk about today. I'm desperately looking for a postdoc. So if you are in the CAV community and want to do a postdoc, please email me, bultan@cs.ucsb.edu. I'm really looking for somebody to work on these topics that I'm going to talk about. And so here's the outline of the tutorials. I'll talk about information leakage and side channels, quantifying information leakage, side channel detection with probabilistic symbolic execution, then model counting, then attack synthesis. I will give a break. I think we have 2 hours. I'll give a break maybe after an hour. And I have 2 short demos to show you things. We have implemented, but I think, you know, the slides also pretty much explain it, and I can share the slides later on. So let's start with the technical part, so which is not a very technical start, but just first, the best example I know for explaining side channels. This is an article in Time from 1990. And I just have to say, I gave you the names of the students before. So these are all slides that my students prepared. So for example, this is something Lucas Bank found, which was, I thought, a great example of side channel. So in this article in Time in 1990, the claim is that the pizza parlors around Pentagon noticed that, you know, when there is some big news going to happen in Pentagon or White House, maybe a military action, there is an upsurge in pizza orders from Pentagon and White House. So because the night before, when there's a big event, maybe a military action, people stay in offices and order pizza. So, and they ordered that, you know, they noticed that the Pentagon orders doubled up the night before Panama attack. And this was similarly observed before the Grenada invasion of Kuwait. So this is a great example of a side channel, because you may say that, you know, the Pentagon, US government has a main channel of communication through their press secretaries. And that is the, you know, public information they release. And there are information they don't want to release. For example, if they have some, you know, important action they are going to do, especially if it's a military action, I guess they don't want to release that information before it happens. But if you look at the pizza orders in Time, you can actually apparently predict when there's going to be a big announcement before that announcement is made through the main channel of communication. So this is a great example of an information leak. And this is kind of the things we are going to talk about, not in, you know, in government actions, but in computing. And side channels in computing are also, you know, well known. You probably heard about the Meltdown and Spectre recent exploits, and these got a lot of, you know, publicity. I'm not going to talk about these today, although the concepts I'm going to talk about are applicable. And I'm actually, the things we have worked on more on software side channels. But the session chair, Chao Wang, has worked on these Spectre and other cache-related side channels, and you can ask him more about those. So the things I'm going to talk about are kind of more general, but they're applicable to any kind of side channel. But especially we focused on, in my work, with the software side channels. So, so what are side channels? One thing is, the first thing is, the side channels is about confidentiality, right? So a program that manipulates secret information should not reveal that information. So that is what you expect. But side channel attacks recover secret information from programs by observing non-functional characteristics. So, for example, execution time, memory usage, memory accesses, you know, and things like that, energy consumption, even network communication can leak information. And so these are the side channel attacks. Look at that kind of characteristic of the program, and then try to infer information about the secrets. So to model information leakage, typically you classify inputs as inputs and outputs as secret and public. And confidentiality is basically information about secret values should not be leaked to public values. And typically in the literature, people use secret high to, you know, to indicate secrets, and low to indicate public inputs. So that's basically the security level. High means high security level secret, and low is low security level public. So I will mention these during the talk. But so there is this concept of non-interference, and the idea there is that there should be no information leakage from secret inputs. And that is ideally what you would want. So non-interference, high secret values have no influence on public values. And This can be checked in some work using dependency analysis, kind of determine data and control dependencies among high and low values, and make sure that low values do not depend on high values. So if you can, show there is no dependency, you may be able to show that there is non-interference, so information doesn't leak. Determining non-interference for side channels could be more complicated. The execution time and enforcing could be also costly, showing that execution time is completely independent of the secret values. Could be tricky and costly actually. So it is a challenge. But we can model the non-interference pretty simply. I have some slides with notation eventually. Hopefully not too many, well, maybe a lot, but I'll say that there is no background needed for the stuff that I'm discussing. All the definitions are in the slides. But so let's say a function, we model the program as a function that takes high and low values and maps it to the low value, basically the public value, right? High and low, high is the secret and low is the public input. And let's say H and L denote the domains of high and low values. So we can now formalize non-interference. We can say that for all high values and low values, basically, if I keep the low value, low input, public input to the program the same and only change the secret value, okay, then public output remains the same. So the public output, the visible output, does not depend on the secret input. So this is non-interference, and if I can show that, then I know that my program is confidentiality property satisfied, and my program does not leak any information. There is a formalization of this. So I'm mentioning these concepts because they are related, and I don't have citations in the slides. At the end of the slides, there's all the papers listed. There is a lot of work in the CAV community also in this domain, and just I'm mentioning things here about hyperproperties. Non-interference is not expressible on individual executions, on traces, which is typically what is done for a lot of things in the verification community, because it requires reasoning about pairs of executions, as I showed in the previous slide, right? So if you look at the definition, it's actually talking about two executions of the program. So, so it requires reasoning about pairs of executions, and hyperproperties express conditions on sets of traces. So hyperproperties is, there are extensions to temporal logics to formalize these concepts, security concepts like non-interference. And so then you can use hyperproperties to express this something like non-interference. And furthermore, you can use this concept of self-composition, which basically the idea is that you create multiple copies of the same program by renaming variables, and then express conditions on multiple executions of the program by referencing variables of different copies of the program. So you are kind of running multiple instances of a program with different variables, right? Instantiate them with different variables. And then you express conditions on multiple executions. So now basically using self-composition, you are reducing hyperproperty verification to property verification. Of course, you are increasing the state space, but it can be done. So then you can use, standard verification techniques to verify a property like show non-interference. This is all great, so good, but there is a problem here because, for example, I'm showing a very simple password checker, and I'll use this in more this example, simple example, variations of it in the talk. So this is just checking if password, there is a guess, the input from the user, and then there is a secret password, and it checks if the guess matches the password and grants access or says error. So this is how you would implement a password checker, right? So there's a secret password, there is an input coming in, and you need to check if the input matches the secret. And if it does match, you will grant access. If it doesn't match, you will not grant access. Now, this code leaks information about the secret password, even though if the guess is wrong, I learned the guess I entered is not the secret. So it does leak information. Non-interference cannot be verified on this program. And this is how you need to do password checking. So there's a secret, but there's a leakage. So non-interference does not work here. So there are other examples where non-interference is not possible and leakage is unavoidable. So password checker is one, but you can consider an electronic voting application where the result of the vote is public and it does leak information, but individual votes should be private, maybe, you know. So you don't want to leak all the information, but some information leak is not, you know, cannot be prevented. Some information leak is going to happen. So there are many practical cases where non-interference is simply not possible, and some information leakage from secret to public values is unavoidable. So that's why, you know, so non-interference is good, but if you can achieve it, but there are many cases it's not possible. So therefore, that's why I want to talk about quantifying information leakage, because we want to quantify how much information leaks. And non-interference says, you know, we want zero information leakage, but that's not practical for many cases. So we want to quantify how much information leaks. And so for that, you know, so that's the thing we want to figure out for password checker. So for example, if a password checker is implemented properly, it should not leak too much information, but maybe there's a mistake in the implementation, maybe there's a side channel, so then it leaks more information than we want. And that's quantifying information leakage. Quantitative information analysis will enable us to detect if there is too much leakage. So that's the, then this is what the quantitative information flow area, research in this area tries to accomplish. So the goal of quantitative information flow techniques is to quantify the amount of information leaked from a given program. And so then side channels is an example of that. Quantifying information leakage through side channels is one example of that. So, so again, just at a high level, so what is the side channel leakage? So we have public and secret inputs to a program, and we have an output, and let's say the output is public. But we also have some observations about the program, which could be execution time, memory usage, and we also assume that they are also visible by the public. So these are not secret values, so we can observe those characteristics. So these observations through like execution time, memory usage are the side channels, and the output of the program is the main channel. And you can use quantitative information flow analysis to quantify leakage through both the main channel and the side channels, actually. But side channels is the more you know, interesting area, where because there are a lot of unintentional leakage through side channels typically. Execution time is one of those, like timing side channels. You can have timing side channels through execution times. And so here is a running example that I'm going to use. This is a password checker. Now there's a little bit more detailed implementation. So it takes two string inputs. High is the secret password. Low is the input that the user entered. And if the low input matches the high input, then, you know, we return true, saying that, okay, then we will grant access. If it doesn't match, then it returns false, this function. And notice that this function implements this through a loop, and basically checks each character one at a time. And if there is any mismatch, it immediately returns false. So starting from the first character of the string, and then completes the, if everything matches, then returns true at the end. So let's assume for this code, it may not be possible, but let's assume that we can actually, by execution time, let's say when we enter, let's say the password is vlab@ucsb, and the input is xxxxx, right? So let's say execution time is 5 milliseconds. Just let's assume that's the case. Now, when in this scenario, so basically nothing matches immediately, the first character doesn't match, and it returns false. So that, let's say, takes 5 milliseconds. Now, if I enter alab@ucsb, still the first character doesn't match. So it will still return in 5 milliseconds, right? Now, if I enter VXXS VLAB, so the first character matches, and maybe let's say the loop execution takes 1 millisecond, which may not be realistic, but let's assume that it takes longer, right? And since I iterated the loop one time and I went to the second iteration before I exit, so execution time went to 6 milliseconds. And therefore, actually, so when the first character matches, I can detect from the execution time the first character matched, right? And if I detect 7 milliseconds, then I know the first 2 characters matched. And this way, actually just looking at the execution time, I can detect how many characters matched. And this is a classic example of a side channel vulnerability. And actually this vulnerability, variations of this vulnerability exist in real code, and actually it cause real vulnerabilities and exploits in important code that accesses secret information. So this is called segment oracle side channel vulnerability. I'll show more examples of this later. And this can be attacked by something called a prefix attack, where each character, you can determine each character one by one and recover the secret password without doing an exhaustive password attack. And so just to tell you, in reality, this basically an attack very similar to that, and a vulnerability very similar to that simple code I showed, exists in real code. And this goes to, for example, Google Keysar library attack. These are some reports on these attacks and exploits, timing vulnerability in OpenID. So this cause really real problems. And so here is it's not a password checker, but it's the same type of vulnerability. It's in memory compare. It's a library function. And you look at this code, it's actually has a similar problem like the one I showed before. What it does is it's comparing 2 memories, but when it's doing the comparison, it's going character by character, and then it returns as soon as it finds a mismatch. So it starts from the beginning. As soon as it finds a mismatch, it returns, so that it does an early termination, like the password checker example I showed. This early termination creates a timing side channel. And this way, for example, Xbox OS, HMAC signature is compared with this function, and this led to side channel vulnerabilities and exploits. So, and this happened in real code. So this is not a toy example. This actually does happen. So this is the part, I wanted to give the motivation here. And I just wanted to ask Chao if there are any questions so far before I get into a little bit of information-theoretic modeling of this information leakage quantification. Chao, are there any questions that I
right now, there hasn't been any question asked on the Slack channel, but I have a question.
Yeah.
So it's very interesting that there is like this pizza example as a motivation for side channel. I haven't heard about that before. What I heard about is people wrap up the electronic devices in a tin foil and try to prevent information from being leaked. But at the high level, I wonder, because this is a frequently asked question, what's the difference between this side channel and the normal information flow security? For example, you can mark the input and output, classify them as high and lows. And is side channel similar to that? Because otherwise you could use, the normal type inference or tent analysis, tent tracking to solve the problem, right?
Yeah, and I think, Chao, the answer to that is, from the way I'm modeling it, actually, you'll see that there isn't much of a difference. I mean, there is difference in details. There is difference in the following sense. So to do the side channel analysis, you need to model the observable execution time, memory usage, things like that. So you need to be able to model those, right? And actually, if you are not looking at side channels, it may be even easier to figure out the information leakage. But the key thing here is this: for quantifying information leakage, just dependency analysis is not going to be enough. So we want to detect how much information is leaked. So that is one critical thing, right? So non-interference, again, you can do just with dependency analysis, maybe, you know, taint analysis, things like that. But you cannot quantify the leakage using those techniques. So that's one thing, quantifying the leakage. But you can quantify the leakage for main channel. Okay, main channel is basically like the output of the program. And, you know, when you return a value. So that would be very similar to the techniques I'll describe. But I guess did we, for example, why I focused on a side channel? Because it's a little bit of a more challenging problem, I think. And also, yeah, it is, I think, for example, in software, there is still a lot of things out there, I think, that's not explored. I think there are a lot of vulnerable software. I think hardware cache related side channels are well known, but still you see the exploits coming out, right? So it's an area which I think requires a lot of attention because I believe there are lots of vulnerabilities there. So that's why we focused on side channel, but I agree that, you know, in principle, leakage through main channel and side channel, you can have similar models. But again, with side channels, you need to model also the, you know, this observable, which is typically not in the semantics, you know, of the program, right? Execution time. So you need to kind of figure out some way of modeling it.
Yeah, thank you. There is now a question asked by Ali, says that shouldn't the attacker have more information about the non-functional property of the program? Like in your password example, how would the attacker know the execution time?
Yeah, so execution time, so there are different attack models, right? So I am going to assume that the attacker can observe the execution time. So there is basically what we are assuming. Actually, the things I'm going to discuss, we are assuming the code that's being used is actually public. So it's like a white box analysis, although there are black box analysis techniques too. So let's say somebody's using public code. So for example, memory compare, it's a library function. You know, I can model it, right? But there is some data that's flowing into that function that's not public. So I don't know that data, okay? Plus, I'm observing the execution time. So as an attacker, I'm observing the execution time. So, and you may say, well, that's too strong of an attack model. But, you know, so it is, so it is, there are very practical cases where this actually causes a lot of trouble, right? Because maybe I'm observing a process that's running in my computer, but I'm not supposed to see some values there, but I can, by observing its time, you know, I can see it. So the assumption is you can observe the execution time. Now you can, but the analysis is general, right? So you can actually, whatever you can observe. So if you cannot observe execution time, maybe there are other things you can observe. And then you can look if there's a side channel based on that. Yeah. So yeah. Okay, all right. Any more questions or should I continue?
That's all.
Okay. Okay, so I'm going to give I'm going to talk about a little bit for information theoretic stuff, then I'll get into symbolic execution-based analysis, you know, so this is, again, more generic part of it. And these are stuff, I have been working on this, I guess we started about 5 years ago, maybe. So I learned these things myself. And a lot of the things I'm using are actually, I learned from papers I read. And I'll list at the end, but like Jeffrey Smith has a lot of, you know, great papers on modeling this, you know, foundations of quantitative information flow. So there are, so things I'm showing are actually, these parts are pretty general. But then when I get into probabilistic symbolic execution, it's kind of, will be more recent work that has been done on this. So, okay, so let me go back to this presentation. And so quantifying information leakage. So how do we quantify information? So Shannon entropy, I'm going to focus on Shannon entropy. And it's what is Shannon entropy? It's a measure of uncertainty about a random variable, let's say X, right? And it's actually, I'll give an example to make it, I guess, more intuitive. But it's the average information gain that you get by observing the value of the random variable. So average information gain, right? So it's the expected value of information gain by observing the value of the random variable. If this doesn't make sense, I'll give an example. right? And it's expressed in terms of bits, okay? Another way to say it, it's an expected value of number of bits required to transmit X optimally. So if you are going to, pass the value of information, the value of this variable, how many bits you need on average, right? So that's another way to look at it. But so, okay, this is a crowded slide, but let me go over it. So I have a random variable X, and it has a domain of values, right? And it takes values from that domain. And so there is a probability of X taking a certain value, right? It has a probability distribution. Now, Shannon entropy, H of X, is described as this formula. It's basically an expected value. It's the expected value. This summation, it's a weighted summation, right? So it's basically multiplying the probability of X having a certain value with this log value here. And it's taking an expected value computation. And this value is log of basically 1 divided by the probability of observing that value. So as probability gets lower, this value inside of the log increases. So this part is kind of the surprise, the amount of surprise, like the amount of information you get by observing, seeing a value, random value variable take a value. So if it's a very rare value, you are surprised a lot, right? So this increases. But then you are taking the log of it, so you're expressing in terms of number of bits in a way, and you are taking the expected value. So that's my intuitive explanation of what this is, but let's do an example. So example is this. So people tell me that in Seattle, it always rains, okay? So, and let's assume that's true. It's always raining, all right? So the probability of rain in Seattle is 1. So that means, so now you can say that means when you get out of the house in the morning and look at the weather, do I gain any information? Well, if the probability of rain is 1, it's always raining, you gain no information, okay? And if you plug this thing to entropy formula, actually it will tell you the information gain is 0 here. Uncertainty is 0, another way of saying. So uncertainty of this random variable, there isn't any because we know its value. It's always 1. Now, Costa Rica weather is apparently a coin flip. It's, rains half of the time and it's sunny half of the time, all right? So now there is information to be gained, right? So when I get out, look at the weather, it may be raining, it may be sunny. I don't know which one it is. I know the probabilities are 0.5 for each, so it's even. So how much information do I gain? If you plug in these values to this formula I had before, entropy formula, this formula here. So you have 2 values for domain is rain or sun, right? And the probabilities are 0.5 for these. And you do this log and everything. What you'll get out of this computation is entropy 1. So it's 1 bit of information if it's evenly distributed, right? So now let's come to Santa Barbara. In Santa Barbara, we are lucky. The weather is almost always beautiful. It's not 100%, but 90% of the time in Santa Barbara, we have sunny weather. And sometimes 10%, let's say it's rainy. Actually, it's probably better than that, but let's say that's the case. So if I give these probabilities, so now the question is, when I get out in Santa Barbara from the house and I look at the weather, how much information do I gain? It's more than 0 because it's not constant. There is some variability, but it is less than 1, right? It's because it's not even because it's most likely to sunny. So it's not as much information as Costa Rica weather. So if you plug into this to Shannon entropy, and Shannon entropy will tell you, well, the information you gave is 0.496 bits of information. So it's a way of quantifying the information gain, right? So that is what it is. And this is exactly the concept we will use for information leakage, to model information leakage, right? So now let's talk about programs. So how can we quantify information leakage? So I'm going to assume secret input and output, public output of the program. And it could be, again, this all could be the main channel. It could be the side channel. So at this level of abstraction, I won't distinguish. But what the program will take a secret value and it will map it to an output value. Okay, so the output could be something returned from the program, or it could be the execution time. I would consider that as an output too, right? So I'm looking at a very high level. So then, secret domain, so I have a secret input to the program, I can actually try to figure out how much information is there for the, this random variable, which is the secret. It has a domain, right? I can look at the probabilities of each value that it can take, and I can use the Shannon entropy formula to determine the initial amount of uncertainty about the secret. So if I'm an attacker, let's say, how much information do I need to figure out to find the value of the secret? So you can characterize that with Shannon entropy. Now, if you assume every secret value is equally probable, right? Then Shannon entropy actually will tell you the entropy is log of the domain size, okay? Log 2 of the domain size of the secret. So if you have a 4-bit secret, then every value is equally likely, then the information entropy is 4 bits, okay? If you have an 8-bit variable, the entropy is 8 bits. So that's the initial uncertainty about your secret, okay? Now, but the program, I run the program now, it takes the secret as the input and produces an output. Okay, so now I can look at the outputs of the program. The output of the program defines the equivalence relation on the secret. So basically, I can partition the secret domain based on the output values. So if 2 secret values give me the same output, I will put them in the same equivalence class, right? So I'll partition the secret domain. Now, looking at the output, I can basically figure out which partition cell that the secret is in, right? So this is the information leakage. So I am gaining some information about the secret. Notice that this assumes you know the code, how the code works, right? But, well, if I don't have the code, well, first of all, I can't have access to the code. Maybe it's a public code, right? So then I can do this analysis. If I don't have access, maybe I can exhaustively test the code. I get the code, I have access to not the source code, but I can run the function. If I can run the function, I can repeatedly run it, look at the observations and the inputs, and maybe establish this equivalence relation, right? So that's like using profiling. Or maybe it's the white box technique and I can figure this out, okay? So by observing the output of the program, we can partition the secret values, right? So if I do that, so now, here is the interesting thing. So how many different, what is the domain size of the output, right? So assume that the output has 1 value, right? It's a constant, right? So let's say execution time. Let's say it's constant. It doesn't change. Whatever the secret input is, it remains the same. Then there is basically, I'm not partitioning basically the equivalence relation, all the secret values are in the same equivalence class. So I gain no information by looking at the output. If the output is constant, I cannot gain information about the secret. And this is exactly non-interference is. So basically, it's a way of looking at non-interference. You don't gain any information about the secret. So basically, there is the uncertainty about the secret remains the same if the output is constant, and this corresponds to non-interference, no information leakage. But that's typically not the case. So now, how can we define how much information is leaked? So intuitively, there is some initial uncertainty about my secret. There is some information leaked, and there is some remaining uncertainty. This is typical case, okay? And equivalently, I can say the information leaked is the initial uncertainty minus the remaining uncertainty after I do look at my output of the program. So that is the information leak, and that's what I want to compute. So an example, so here is a simple code. It takes a secret value, and it takes a bitwise, and so let's assume it's a 32-bit unsigned integer, and this constant here, hexadecimal constant, is value 15, and is bitwise AND operation there, and it prints basically last 4 bits of the secret, okay? Now, this is through the main channel. Chao asked, does it matter main channel or side channel? So in this case, actually, I'm talking about the main channel. It's just printing last 4 bits of the secret. Now, this output, if you look at the way I described it, this function partitioned the secret domain to 2 to the 16 equivalence classes, right? Based on the output. And there are 2 to the 28 values in each of these equivalence classes, right? So there are 28 bits of information still left in secret, uncertainty, right? But 4 bits of it is leaked. So this is exact. So what I would expect is this program leaks 4 bits of information, and the initial uncertainty is 32 bits, and remaining uncertainty is 28 bits. So we want to formalize this concept. And you can formalize this using entropy. Now this is, again, some more formalized. The whole thing here is that now entropy can be also generalized to conditional entropy. So what is the uncertainty of secret given the output observation? So this is the concept, and I am going to use conditional probability here. So this works. It's just use probability, basic probability theory definitions of conditional probability, and using those, you can actually get the conditional entropy. And if you do this calculation, you will actually see, for the previous example, you will compute that the conditional entropy for secret is going to be 28 bits. So now, so here is the formula that basically corresponds to the intuitive thing we said. So initial uncertainty of the secret minus this conditional entropy. Basically, what is the remaining uncertainty on the secret given the observation? If we take that difference, what we get is called mutual information. It also happens to be symmetric. So, you know, mutual information between secret and observable. And this O we call observable. In side channel analysis, it's not necessarily the output, right? It's the thing we can observe. And this basically tells you the information that's leaked from the observable about the secret, right? And it gives you the difference between initial uncertainty about the secret and the, you know, the remaining uncertainty about the secret after you made the observation. So, and that exactly corresponds to the intuitive concept of information leaked as initial uncertainty minus remaining uncertainty. So now you can have 3 simple examples. For example, here's a function that just prints 10, takes the secret as input. Its output has nothing to do with the secret. So initial uncertainty about the secret is 32 bits. After I observe the output, which is always 10, the remaining uncertainty is 32 bits. How much information is leaked? Nothing. It's 0 bits of information leaked. Now this one prints S plus 10. So it adds 10 to secret and just prints it. Initial uncertainty is 32 bits. How much uncertainty is left after I observe the output? No uncertainty is left because the secret is output minus 10. So I exactly know the secret once I observe the output. The equivalence class, you know, the size of each equivalence class is 1. So there is no uncertainty left. So therefore, the information leaked is 32 bits. And the example I had earlier prints the last 4 bits. Initial uncertainty is 32. 28 bits of observation I gained after observing the output. Sorry, remaining uncertainty is 28 bits after I observe the output. And the information leaked is 4 bits, right? So by observing the output, I gain 4 bits of information. Now, what about side channels? Okay, so now I can convert this to a side channel example where now I'm not printing anything. I'm just actually changing the execution time based on the secret. So this, you know, program sleeps for S seconds. Well, it doesn't have to sleep. This is a silly example, but it does some computation which depends on the value of S. So if I do that, then, you know, this is basically would leak the information about the execution time, will leak information about the secret. Or this one looks at the last bit of the secret, and then it sleeps different times based on the last bit of information. So they don't return any output, but they do leak information. They leak information from the execution time. So how much information they leak? So this one, execution time is exactly dependent on the secret. So there is no uncertainty left about the secret once I observe the observable, and the information leak is 32 bits. Here, you know, execution time leaks 1 bit of information, so remaining uncertainty is 31 bits. I learned the last bit of the secret. Now you may say here, well, how can you really tell the precisely the execution time? Because there could be noise. There's all sorts of things in the execution time. What is the, you know, how precise can your measurements be? So that is true. I'll at the very end mention this before the tutorial is over. You need to do some noise modeling to actually precisely capture these things. But you could do noise modeling and you could still get this conditional entropy and actually quantify the information leakage. So you may require some profiling to do that, but it's doable. So I just want to point out a couple more things before I get to the symbolic execution part. If you assume that the program is deterministic and the only input is secret input, then given the secret value, the observable, there is no uncertainty on the observable, right? The program is deterministic and the only input is the secret. If I assume that, there is no uncertainty about the observable given the secret. So the information is entropy is 0. So now I told you that this mutual information was symmetric. If I use this formula from the, just doing a little bit manipulation here, so mutual information leaked can also be written as initial uncertainty about the observable minus the conditional entropy. And that, since this term is 0 here, conditional entropy given the secret, what's the uncertainty about output? It's 0 if it's deterministic. So therefore, actually, for deterministic programs, you can say, and the secret is the only input, the information leak is exactly the entropy of the output. How much, the entropy of the output gives you the information leakage. Okay. So a couple of other things I want to add before closing this section. There are other concepts of entropy, like guessing entropy, which quantifies the expected number of guesses required to guess the secret. Mean entropy, which kind of quantifies the worst case information leakage rather than the average case, which Shannon entropy does. So those could also be used and have been used for quantitative information flow. So that was kind of the information-theoretic background for quantifying information leakage. So now I'm going to get to program analysis and probabilistic symbolic execution and all that stuff. But I wanted to take questions if there are questions about the parts I discussed so far.
This is very fascinating. I mean, the similar concept that has been used in information theory, right, by Shannon, and you're able to just look at a computer program and then try to calculate the leak. That is really fascinating. I have a question related to the conditional entropy. That is the way that you use to calculate how much leak is there in the program when it's being executed. So the related question is, well, you mentioned you have to allow a certain amount of leak in practice because all program leak information. But then the question is, once you find out that the leak is non-zero, how do you know that it's possible to have an attack or it's a secure? What is the threshold you use to determine that?
Yeah, this is a great question. This is good. So Chao, this thing we worked on was motivated. I got into this. There was a DARPA program, STACK program that Corina Pasaran and I had a joint grant on it, and also from Vanderbilt, CMU, and UCSB. And this is the problem that we struggled all the time: how to quantify the leakage. I mean, we use Shannon entropy, but what does it mean? And it gets very frustrating. So, but I gave you the definitions. But eventually, we went to attack synthesis just to get to, but interestingly, attack synthesis uses these concepts. I'll tell you at the end of this tutorial. But we generate attacks, meaning, so again, here we are not trying to be, malicious users, right? So the analysis we are doing is to find vulnerabilities, demonstrate vulnerabilities, and so that you can fix your code. But if I show you an attack, an exploit, a sequence of inputs that steals the secret, then proof is in the pudding. I don't have to, here is how I get your secret. And therefore we can stop talking about, so I told you, here are the number of steps and I got your secret. So that's what we went eventually to make it very clear, right? But you are right. So when you have this, but you can imagine scenarios. So I don't want to completely dismiss this. You can imagine the scenario. You can say, look, I don't want to leak more than 2 bits. And what does that mean? I don't want to leak more than 2 bits. Well, it depends on if you are using Shannon entropy or mean entropy, it will mean different things. So you need to understand, what entropy concept you are using and what are the implications of that. But if you have some understanding of that, I think that could also be used. but I agree there is some, it's a little bit of like, it doesn't directly relate to maybe an attack. But if I synthesize an attack, then I'm actually showing you, look, here is the leakage because there is an attack and it gets the secret in this many calls to your function, right? So then it's very clear. So
yeah, thanks for the clarification. Here is another question asked on Slack. Kaldeep asked, for what applications it is reasonable to assume that we have access to the source code? I guess, I mean, for crypto algorithms, I know that all the crypto algorithms people are using are actually open to public. You actually have the source code, the algorithm, everything. In your case, you're analyzing Java code. Is it a reasonable assumption that you would have the source code?
Well, Java has, again, you know, memcompare is a great example. I mean, there are library functions that leak information. So we actually did some other analysis on, we have recent papers on JIT leaks. From JIT, there is information side channel leakage. My student Tegan Brennan worked on that. And so she's graduating. And so she looked in Java library code. It would help you to know which functions in Java library, you know, leak information. So don't pass secret information to those functions, right? So that's kind of one application. But again, I don't think you can do these things. So things I'm going to describe are white box. So you can do this internally. I'm a software developer. I want to know if my code leaks. So I am trying to fix my code. So that's one way of looking at it. Or if from the attacker side, attackers could have public code, access to public code that you use. So they may do it based on that. Plus, they can do profiling-based techniques, which I'm not going to discuss too much, but that's also doable. And this quantifying the leakage would still apply there.
Thank you.
Okay, so I hope I didn't bore you too much here because the you know, the exciting stuff is just starting, I would say, because this is the stuff that, you know, we worked on. I mean, these are the foundations. They are also very exciting. But now I think we are going to get to more maybe CAV, you know, the stuff that a lot of people are familiar here in the CAV community. So symbolic execution, for example. And there are, you know, so I'm going to focus on symbolic execution-based techniques, but other techniques can also be probably developed related to quantitative information flow and has been developed. So there are other works. So now I'm going to look at again, the same, you know, this is now a pin checker. I'm calling it a pin checker because we are just going to have 4 characters here or 4 numbers. It's an array of size 4, and there is a guess and there is a pin, right? So let's say this is a 4-digit pin. And this has the same vulnerability. It's doing early termination. So there is a information leakage from the execution time. And so here is the symbolic execution tree for this piece of code. Very simple, right? First character is compared. If it doesn't match, returns false. And there is the path condition, path constraints on the inputs. What constraint on inputs make you take this execution path, right? So the first characters don't match. Now, this is the second execution path, goes through, you know, first character matches, second character doesn't match. And now this is the path constraint for that. Or first 2 matches, third doesn't match, first 3 matches, fourth doesn't match, and all match. And if all match, it returns true, right? Otherwise, it returns false. So here are 4 execution paths. So now symbolic execution, standard symbolic execution would generate these path constraints for you and will tell you which paths are feasible in your program, right? I assume a lot of people know that, but even if you don't know that, that's what symbolic execution does, right? So it generates path constraints on the input, and you know, tells you which paths are feasible. Now, we are going to extend symbolic execution to probabilistic symbolic execution by determining the probability of executing each program path. So how are we going to do that? Let's say PCI denotes a path constraint for the ith program path. And let's say the number of solutions to that constraint is this, right? Okay, so I'm using that. Now, that's the number of solutions, number of satisfying input values, you know, number of input values that make that path constraint true, right? It's basically just, you know, how many values, input values satisfy that path constraint. It's as simple as that. So let's say we have that value. And let's say D is the domain, input domain, and the size of the input domain. Now, what is the probability of executing a path if we assume uniform distribution over the input domain? Okay, so that's what I'm going to assume, uniform distribution. But it can be generalized, but I will, in this presentation, I'll focus on uniform distribution. The probability of executing that program path is this, right? You count the number of solutions, assuming uniform distribution, number of inputs that satisfy the path condition, you divide that by the domain size, you get the probability of executing that program path, okay? So that's what we can do. So this is where we are going to get into model counting, you know, I'll talk about after this section. So probabilistic symbolic execution of the 4-bit, let's simplify our program, very simple. We had a 4-digit, let's say it's just binary digits. It's like 4-bit, all right? So I have a pin number and I have a guess. So pin is the secret, guess is the, you know, public input. So each is 4 bits. So my domain size is actually 8 bits, right? And each path constraint, I can compute the probability like this. So let me show you the path constraints now. So I have 5 path constraints, right? First character doesn't match, second character, first matches, second doesn't match, blah, blah, blah. All of them match it in the last one. And now I can, so what I need is to count the number of solutions to these constraints. And this is called model counting, right? So I need a tool that counts the number of solutions to this constraint, for example. Now, first bit doesn't match. I have 256 values. So there are going to be, this is going to eliminate half of the cases. So if I count the number of solutions to that, I'll get 128, okay? So among these 256 values, 128 of them, the first bits of the pin and the guess doesn't match, right? And what's the probability? If it's uniformly distributed for the pass and pin and the guess, then the probability is 0.5. So if I'm randomly picking pin and the guess, I'm getting actually 0.5 probability I will get this execution path. Now, what is the number of solutions for this path constraint? And that one is 64, actually, and the probability is 0.25. And I can just do this for all. And the last one is going to, last two are going to both have 16 solutions, and their probability is going to be 1/16. So this is the, basically, you know, this is called probabilistic symbolic execution. So it's an extension to symbolic execution. In addition to computing execution paths, you can actually associate a probability to each execution path. And to do that, all you need is a model counting constraint solver. So given a constraint, how many solutions does that constraint have? If I can do that, I can compute these probabilities, right? So now this is good. So we can, so now how does this apply to quantitative information flow? So that's what I'm going to get to, and side channel analysis. So I'm going to extend this to side channel analysis. Now notice that I got probabilities, and for information leakage, for entropy computation, I needed probabilities. So probabilities get me very close to you know, information leakage analysis, but I also want to do side channel analysis. So I want to extend symbolic execution to keep track of observable values, and for example, like execution time or memory usage. So I'll call these observables. And one thing you need to do is to track this observable value. So this was an extension to SPF, Java Pathfinder, symbolic Pathfinder is an extension to that. This is Corina Pasaranu extended symbolic Pathfinder with this kind of analysis where they were putting observable values. So this is the project we collaborated on. It keeps track of, for the timing side channel, it keeps track of the number of instructions executed during symbolic execution. So now in this extended symbolic execution with you know, time tracking, let's say, in addition to getting a path constraint, I also get an output observable value, which is the number of instructions executed for that execution path. So that's, I'm denoting with O here. So in this case, it's 3. In this case, it's 5, 7, 9, 10 instructions apparently. Now, this observable doesn't have to be the execution time. It could be memory usage, but then you need to keep track of memory allocations. And you can, so in symbolic Pathfinder, this is done by adding listeners. So you need to kind of add these listeners to the symbolic execution and either keep track of the execution time or the memory allocation. Or you can use a public output. So then you need to keep track of the value of the variable. So that can also be done, right? So this observable could be something you print maybe. So you need to keep track of that. But what we are assuming now, in addition to path constraint, we get this observable value. So if we do that, so if we assume 4-digit pin, now in addition to having this probabilities, I also have these observable values, which is number of instructions executed. And it says 3, 5, 7, 9, 10 for this. So now I'm assuming these instructions are distinguishable. Now you may say, okay, well, how do you know 5 instructions versus 7 instructions? That seems too small. You won't be able to detect it. I know. So you can put thresholds, actually. You can say, no, it has to be 1,000 instructions different. Otherwise, it's in the same equivalence class. So we could merge these path constraints to do that. And we have that actually implemented. But you can even do some more sophisticated things where you model the noise on the execution. I'll mention that at the end. So, but now we have this table. Notice that I have my observables. So now I'm getting very close to what I wanted to do. Remember that I told you for deterministic programs, entropy of the observable actually tells you the information leakage. So all I have to do is now I have my probabilities, I have my observable values. All I have to do is apply the entropy formula to determine the leakage from this program. And if I do that for this program, using these probabilities and the fact that there are 1, 2, 3, 5 observables, I get the leakage of 1.87 bits, okay? So that is the information leakage from this program through the timing side channel. So you may say, well, what does that mean? I don't know. 1.8 bits. Well, it leaks, based on the entropy distribution, it reduces the uncertainty about the secret, looking at one execution with 1.87 bits, right? So the remaining, you can say that we had 4 bits of uncertainty initially. Now we have 2.1 or something, right? So we leaked information. Now, but you may say, well, I don't know. I find this fuzzy. If you're not convinced, you can compare this with a password checker, which is actually doesn't leak from side channel. So this doesn't leak from the side channel because notice that it doesn't do early termination. It actually processes the pin and the guess till the end. It does not terminate early, first mismatch, just keeps a flag, and basically execution time is constant. Now you can say, well, how much information does this leak? Well, I can just look at the main channel in this case. Main channel is it's going to return false or true, right? So if it returns, so there is still going to be some leakage, and I can even quantify that through the main channel. What's the leakage? And in this case, leakage is actually 0.3 bits. So notice that there is a significant difference, right? 1.87 versus 0.3. So it will help you compare programs. So you can say, well, this leaks less. So I can see there's a higher leakage here when I implement it this way. This doesn't leak from the timing side channel. So this is basically quantitative information flow, gives you some quantification of the information leakage and comparison. Now, again, this pin checker thing is not a toy example. It does exist in reality, this kind of side channels. I mentioned it. And if there is no leakage, and let's have a 16-digit password, okay, ASCII characters, let's say 128. So if you don't have a side channel, so execution time is constant, no early termination. To get the password, you will need 128 to the 16 tries in the worst case, okay, to get the password. But if you have the early termination side channel, it becomes this segmented oracle that I mentioned. You can do a prefix attack where you detect the first character of the password, just focus on the first character, figure it out, and then go to the next character, okay? And an attack like that works. I'll show an example at the very end. And now you can get the password in 128 times 16 tries, as opposed to 128 to the 16 tries. So this is a huge difference in terms of how vulnerable the code is. And again, this is a very realistic case actually that you can detect. So so that's the I wanted to show you, and I'm going to go do another stop here, and I'll if you have any questions about this, I'm happy to answer, and I'll also try to do a very short demo about this. So Chao, are there any questions? And after the demo, we'll give maybe a 5-minute break. So Chao, any questions about this part?
Yes, there are 2 questions on the Slack channel. The first question was asked by Mohammed. So he said, this is a very interesting talk. Does these definitions of entropy and conditional entropy also apply to non-deterministic program? For example, there could be some programs that have certain kind of non-determinism. Maybe certain input signals have certain probabilistic distributions, and in that case, would a conditional entropy apply?
So yeah, I mean, I think this can be generalized to non-deterministic programs. We do actually have, at the end, I'm going to mention, we do have noise modeling. And so there is non-determinism in the analysis we do. I will mention at the end. And we do noise modeling. So noise brings in non-determinism. And we still use entropy concepts. And I'll mention that briefly at the end. And you can generalize it. So we didn't just focus on deterministic programs for this. And I decided, by the way, I'll do the demo after the break so I can set it up, a short demo, and then I'll continue the other parts. But so let's have questions and then have a 5-minute break, right?
The second question was asked by Kaldip. Do we care about individual probability values or only the entropy value?
To get the entropy value, I use probability values, plug it into the equation to get the entropy value. So I compute the entropy value using the probability values, right? So let me show that here. So if you look at this, so basically what I'm doing is literally I'm using, so here's the thing. So I'm really getting these probabilities. I get the path constraints. I count the number of solutions. Divide by the domain size. So this is the counting of the number of solutions for the path constraint, this row here. I get the probabilities, right? I take those probabilities, plug it into the entropy formula. That's exactly how I get. Now you may say, if you say, well, 3 to 5, let's say 2 instruction difference is not big enough to be observable difference. You can actually merge these path constraints. So you can put a, you can merge the path constraints based on how different their execution times are, and then count the combined path constraints. This is actually what we do in implementation of this. And then accordingly, you can get the entropy based on that. But literally what we are plugging is the model count, probability value, and then compute the entropy, right? And that's how we quantify the leakage.
Okay, so the next question is asked by Ian. Thank you for the interesting insight, but can we actually decide only based on entropy how good the implementation is? Or do we need something to compare to? I guess probably you've alluded to the fact that you could use this to compare different implementations, right?
Yeah, so I mean, the cool thing is we can compare different implementations, right? So this is the one that has the side channel and it tells 1.87, and this one leaks 0.3. So you can do a comparative analysis. You can say that, well, look, information leakage increased in this program. So you can do that. But again, the next thing you can do is attack synthesis, which I'm going to talk about at the end. And then, so that is, we could also do that. So if we do attack synthesis, then we actually get the, attack. So you can say a program which is a shorter attack is more vulnerable than a program that has a longer attack. So that can be another way.
Thank you. The next question is asked by Subesh. I think there is some kind of independence assumption. For example, what if the information leakage is different for positive or negative input values? I mean, one variable, sometimes it could be 0, sometimes it could be 1, and whether the entropy would be different, right? I guess that's what you mentioned, the conditional entropy, right?
Yeah, so, yeah, I mean, this is, symbolic, the way to think about this, the symbolic executions captures the semantics of what is going on, right? So I'm building on symbolic execution. So everything is taken into account, all the program behaviors. So of course, it has the limitations of symbolic execution. So if you said, is this sound analysis? Well, it's not because I didn't do symbolic execution doesn't give me the full execution. If the, I cut the execution depth, right? So when you have unbounded loops, input dependent loops, unbounded recursion, I need to stop the symbolic execution at some point, right? So I'm not doing a sound analysis. This can be extended to sound analysis, though. There is still work to be done there, right? So it is, but currently what we have is actually is not sound. So.
Yeah, there are a few other questions, but I think as you keep going to the next section, maybe it will be clear what the answers are. So.
So should we take a 5-minute break and stop back at 9:15?
Sure.
Okay, so I'm going to then, do you want me to share the slide? So we'll...
yeah, let's just share the slides and show.
Okay. Short break. So we are going to be back at 9:15. So it's 9:11 now, 4-minute break. All right?
All right, thank you.
All right. I think we'll get back, Chao. That's okay. All right. So I want to do a very little demo. So let me see if it works. So just to, so I'm going to share a different screen. Let me see. Okay, so let me share this screen. So here's our, so let me show you simple Java code. This is just to show you that we implemented this stuff. So, so there is the, here's a password checker, does early termination, uses caret, compares its string, takes 2 strings. We are restricting the length of the strings to 4, and compares the input string with the password, which is supposed to be secret, and then does early termination. And that's the Java code. Here is the driver, SPF driver. SPF is a extension to the JPF, right? So it has low and high. Those are the inputs, and those are symbolic strings. It uses the ABC, our model counter I'm going to talk about next, actually. And it uses, model length bound 4. And now if I run this thing using JPF, now, which is again a symbolic execution tool extended with probabilistic symbolic execution using model counting plus this entropy computation based on by tracking observables, all right, using the timing listener. It's counting the number of instructions. So if I run this early termination one, it basically computes path constraints, and then the path constraints are listed here. So here are the SMT formulas for the path constraint. This cost is the number of instructions it executed for that particular path. Here is the path condition, and then bound is 4 for strings of length 4, and model counting time and count. So this is the how many solutions it found, all right? And then, so notice here now, it lists the different costs, timing, observations it, recorded, and count, and the probability. So now, if you look, so this is long, right? So, but I can just explain to you from here what's going on. So this is a 4-character password, right? So the most likely scenario, if the inputs are randomly chosen, both the password and the input, the first character is not going to match. And that's basically what we get. That's the most likely scenario. And if you randomly pick 2 things, the first characters don't match, and we get that. Now, the second likely scenario is the first characters match, and we get a probability for that. And the 2 characters match, 3 characters, and then all 4 characters match, right? So we get all these probabilities, right? And based on that, it does the entropy computation, and we get 0.24. So this is now less than, of course, what we observed for the bitwise side channel, but because, again, the domain is much larger, so getting matches are less likely. But now let's look at another example, which actually does an implementation that actually has constant execution time. So this is the secure version. This is exactly does what I told you before. To fix the side channel, it's actually not returning early, and it executes exactly the same number of instructions if the password matches or not. So then if I do the analysis, same analysis on this one, right? So I'm going to run this now, secure implementation with, the Pathfinder, and it will compute, and it will, compute all the paths again, symbolic execution, does the model counting, and basically it says, look, there is only one cost. Each path has 143 instructions, and therefore the probability is 1, so entropy is 0. So basically it didn't gain any information from the timing observation, right? So this is basically implementation, and and we had done a lot of code with this. I'll show more examples at the end with the attack synthesis, but so just to show you that this implementation. We have the implementation of this, and it does work, and it does what I told you. So now I'm going to get into the rest of the presentation and talk about, sorry, get here, talk about model counting, which is the technique that enables us to do this probabilistic analysis. And I love this topic. So I mean, this was such a cool thing for me to work on, because we have been doing constraint solving in my lab, and this model counting was a very interesting extension for us. So we started working on it. And then when we used it for side channel analysis, it was like a great application. So everything kind of we worked on came together for this work. So that's why we kind of love it. But so I'm going to talk about now in this part, automata-based constraint solving and model counting. So this is the enabling technology that makes us, to do that side channel analysis I talked about. So what is going on here is this: we take a formula, and I'm actually our current solver. It's called ABC, Automata-based Model Counting Constraint Solver. ABC currently handles linear arithmetic and string constraints. Okay, linear arithmetic theory and string theory. And there are, I mean, I think our string operators we handle are pretty extensive, but still there are limitations, and it's not always precise. I won't get into too much on that, but the very cool thing it does is it takes a formula, and it can, from that formula, it will give you a counting function, which basically when you give a bound, it will count how many solutions, it will tell you how many solutions there are for that bound. So it can do this for integers, it can do this for strings. So it's a model counting solver, which is the key thing I need to get the probabilities right. So how does it do it? It's an automata-based solver. So, well, it is the constraints we handle, but anyway, so this is like, there is some linear arithmetic here. You can see linear arithmetic, we can do arithmetic terms. It has string terms, regular expressions, and string operators. It has terms, constraints on strings like match, contains, begins, ends. But it can also have on strings like length that give numeric values, index of, last index of, and then you can use integer variables and string variables and mixed constraints too. So it can handle a bunch of things. Now, we used automata-based constraint solving. All right, we use automata to represent constraints. And you may say, why do you do that? Well, the reason we do that, okay, first of all, we did this before we were doing model counting, because it's a representation that has certain advantages. It's good for, certain problems, automata-based constraint solving. For strings, for example, there are certain things you can do with automata that are, it's very powerful, and using other techniques is actually more difficult. So we have been doing automata-based constraint solving for a long time. But for model counting, there is a huge motivation, because if you construct an automaton for a set of solutions of a constraint, then model counting problem becomes path counting, because what you are doing is counting the accepting paths in the automaton. I'll show you more on that. It's a beautiful solution to this model counting problem. But so our initial thing is, given a constraint, generate an automata that accepts satisfying solutions to this. So now this, I can talk on this a whole couple of hours, but I'll give you a very short overview of this to you. So we can handle both string and integer constraints. So for example, constraints like, well, string variable is equal to a string. We can do integer terms, linear arithmetic, like integer variable I equals 2 times j. Or we can do terms also on combinations. I don't know why I missed that. String and integer variable. So for example, we can say length of variable v is equal to some integer variable I. So we can do constraints like this. So in string terms, integer terms, and mixed string and integer terms. So basic string operations like string equality, well, you can construct an automaton for that. Well, match, for example, regular expressions, you can do, standard construction of automata from regular expressions. So for example, saying that variable v matches this regular expression, you can construct the automata that accepts all solutions for that regular expression, right? And that's such, that is the set of values for variable v. Or you can do, you know, now you can say, okay, I want all the strings that doesn't match that regular expression. I can use automata complement to compute that. So automata operations, standard automata theory. More complex constraints can be solved by creating automata for each subformula and then combining their results. So for example, I can have this constraint. I have a string variable where I don't want it to match to this regular expression, and length of the variable should be 2, okay? So what are the solutions for that? Well, I can construct this, not match regular expression AB star here. That's the automaton I had from the previous slide. Length 1 is also easy. So I can say, all the strings of length 2. I'm assuming here, just to simplify, the alphabet is 2, but anyway, so we can do either way. Just the alphabet of A and B. But so this is the automata for that. So now, but it's a conjunction of those. So now I can use automata product to actually get this automaton, which is actually the set of solutions to this constraint, right? Actually, there's, yeah. Okay. So for multivariable constraints, we can generate. So now, what about if you have multiple variables? So this is an interesting case where V equals T, for example. I have 2 variables, 2 string variables, V and T. So assume again alphabet of just A and B. So I can construct these 2 automata. Basically, V can take any value, T can take any value. So if I construct 2 separate automata for these are both valid, which is great. But then if I say V is not equal to T, V can still take any value, T can still take any value, but their combination, like, they should not be equal, right? This one says they should be equal, this one they should be not equal. But notice that the automata I'm getting for each individual is the same, okay? Because they can't take any value. But now if I take their combination, automata product, I'll still get the same result. Basically, they can't take any value. So this is not good because it says, V equals T and V not equal to T are satisfiable, right? So this should not be satisfiable. So basically, keeping separate automata for each variable, if you do what I told you, it doesn't work, okay? It gives a very bad over approximation. So it basically would approximate because it loses relations among variables. So what you need to do is what we call multi-track automata. So generate, basically create an automata where it accepts tuples of strings and each track represents value of a single variable. So the best way to show it with an example. So this was the single track automaton. Instead of that, what we are going to use is a multi-track automaton, which tracks the value of V and T, 2 variables at the same time. So it's reading 1 character from each variable at the same time. So it's the alphabet is the product of the alphabets of 2 variables, right? So it's a bigger alphabet. And it's basically ensuring that they actually have the same value. So if A, for example, the A comma B goes to the sync state. So I'm not showing the sync state here. So this actually exactly keeps the fact that A and B are, V and T have the same value, right? So now preserves the relations among variables. Using this, I can represent V equals T with this automaton. And I can represent now V not equal to T. I need to do automata complement. Now this gets a little bit complicated. We are using multi-track automata. We need padding symbols. If a string, one of the variables is shorter than the other one, I need to read still something on that track. So this lambda thing you see here is actually a padding symbol, all right? So it is not from the initial alphabet. So I extend the alphabet with this padding symbol, and I pad the, the track at the end to make sure that they're of the same length. But this can be done. So what we have now is actually a representation of V equals T, a representation of V not equals to T, and this is precise representation of these constraints. And now when I do the product automaton on this, actually I get an automaton that does not accept any string. The initial state is not accepting and there's no other transitions. So this is exactly what I want. Now the language is actually empty and this constraint is unsatisfiable. So again, automata-based representation can be done, and it can be extended to multi-track to keep relations among strings, and then we can do combinations of strings too, formulas too. Now, multi-track automata can also represent linear arithmetic constraints. So there is an extension. We worked on this long time ago. Others worked on it. So there is known results on this. Each track represents a numeric variable. You can use 2's complement. That's what we use. And then you can read from, there are different representations. You can start from the least significant bit or the most significant bit. So, so we start from the least significant bit and use 2's complement, and you can represent, for example, I equals j, numeric variable I equals j. So this accepts binary representation of values of I and j. Okay, so it's a automata that accepts numeric constraints, solutions to numeric constraints. And you can do I not equals to j, and then you can do I equals 2 times j. So this is an automaton that's accepting this solutions to this constraint on tracks I and j. So the first track is the variable I, second track is the variable j. So you can also this kind of stuff. Very cool. So here's an example. Oops, my animation is messed up, so let me just finish it. So here is a constraint that is a little bit complicated. Let me explain what's going on here. So this is a constraint that's a combination of multiple constraints. It says string variable v is constrained by a or b star, right? Basically, which means it's a or b. Alphabet is restricted to a or b. And it says length of the variable v is I, integer variable equals to the integer variable I, and I is equal to 2 times the value of integer variable j. So now this basically says that I's value has to be even, length of the string variable v has to be even, right? Because I equals 2j because of this constraint, and then v should only accept a and b. So our constraint solver can handle this. It will generate one string automata. So we keep one string automaton and one numeric automaton. And here it's actually accepting even numbered, strings of length with even length, okay? And of any string of A or B of even length, right? So that's what it's doing here. And this thing here, which is hard to understand what's going on, but it's actually making sure that the length of v is equal to I, okay? Plus I is equal to 2 times j. And the track here, VL is an auxiliary variable, which denotes the length of v. And we use a track for that, and it accepts that this constraint. So together, these two automata actually represents all the solutions to this constraint. The solutions to v are accepted here. Solutions for I and j and the length of v are accepted here. And there is a whole source of papers on this, how we synchronize these automata and all that kind of stuff. But there is an implementation of this. Now, the next part of this is how to do model counting after you do that, right? So if you believe me that I can construct automata, and there are some caveats here, we can't do all string operations precisely. So typically, if there are, depending on the constraints, sometimes we will get over approximation actually, right? So, but we always over approximate. So, but for some class of constraints, it will be precise, but we can't guarantee precision. We will over approximate sometimes. So, but now let's get to the model counting part. So if I get a automata that accepts the set of solutions for a constraint, can I do model counting? And here is the thing I want to do. Here is an automata for this constraint, which is x should not be 0, 1 star. So this one says x in 0, 1 star, and this one says not. So here is the automaton for that. And I'm just using 0, 1 here as the alphabet symbols. And here's the automata for this constraint, right? Fine. Now, what I want is to generate a function which, given the length bound, it will count the number of paths with accepting paths with length k. So initially, is there an accepting path of length 0? And the answer is no, there isn't, because starting state is not accepting. Now, is there an accepting path of size 1? And the answer is yeah, there are apparently 2, because 0 goes to an accepting state, 1 goes to an accepting state, so there are 2. And how many accepting paths are there of length 2? And there are apparently 3, so 1, this is 1, 0, 0. This one is 1, 0 is another one, 1, 1 is another one. So there are 3 accepting paths. So what I want is to generate this counting function. So now how can I do that? And if you watch the movie Good Will Hunting, which is kind of an interesting movie, it got Academy Award for some stuff, right? So where there is Will Hunting is a very talented custodian at MIT, and solves the problems posted by a MIT professor. And then in the movie, you see this problem. And actually, the problem that this MIT professor posts on as a challenge to students is actually this path counting problem. And he's very surprised when somebody solves it, okay? That's one of the movie plots. So this is exactly the problem we want to solve, path counting, okay? So, and Will Hunting is able to solve it. So we'll do exactly what Will Hunting actually does to solve this problem. So what you can do is you can count the number of accepting paths using matrix exponentiation. The matrix you use is the adjacency matrix, okay? So you take this automaton, you look at adjacency matrix. Well, okay, first we need to do one transformation. I'll combine all accepting states to one accepting state with a lambda transition. Let's say, this is like consider it like an epsilon transition. Okay, I'm just going to go to a new accepting state to make it easier. And now I will generate the adjacency matrix for this. So now all I have to count is the number of paths from starting state to this single accepting state. Okay? And adjacency matrix is, I'm showing here on T, right? Basically, number of edges from I to J. So I of J in the T originally, right? So for example, this is from 1 to 1. There are no self loops from 1 to 1, so there is 0. There is one edge from 1 to 2, so I have 1 there. There's one edge from 1 to 3, I have 1 there, so that's 1. In the first row I'm looking at, there's one edge, there's no edge from 1 to 4, so this is 0. Okay. Now T square is the matrix. I multiply this matrix by itself, I get T square. I multiply T with 2 square, I get T to raise to power 3, right? So I'm doing matrix exponentiation. This is matrix multiplication, basically, right? So now here's the interesting thing. If you look at this thing here, which is the number of paths from node 1 to 4. This shows the number of paths, from 1 to 4 with a single edge. This one shows 1 to 4 with 2 edges. And this one with single edge actually corresponds to accepting paths of size 0. So here's what I'm saying. So this value here in this matrix, T matrix, this value is the number of accepting paths of size 0. And it is 0 as we accept for this automaton. That's what I just showed before. And the number of accepting paths of size 1 is 2. Number of accepting paths of size 2 is 3. And number of accepting paths apparently of size 3 is 8. So I can compute this function that I told you that I was trying to compute in the previous slide. So this function here, oops, I went too far back. This function here I told you on the automaton, I'm computing it using this matrix exponentiation, okay? So, and this is great. There is even more sophisticated techniques to do the same thing. There is something called generating functions that you can compute. And this, I won't get into details of this, but you can use generating functions, and you can generate a generating function for a graph using the determinant of the adjacency matrix. And it will, this is the formula here. And for this automaton, it will actually generate this generating function. Then you can do the Taylor expansion of that generating function. And if you look at the coefficients of the terms by magic, there is the proof of this. This is a well-known result, I think, long from, before computing started, well-known result in math. You can actually, from coefficients of this Taylor expansion, the coefficient of the 0 term is actually corresponds to the number of paths of size 0, length 0. Coefficient of the first degree term is the number of paths of size 1, and blah, blah, blah. So you can compute all that. And this is exactly Good Will Hunting here in the movie. You see here's the solution of Good Will Hunting wrote, the matrix exponentiation, and using the generating functions, you can compute this. And the professor is impressed. So automata-based model counting, we implemented this. It does work. It's very, but it will have scalability issues. There's exponential blow up in automata representation. So we had to do some extensions to make it scalable. So we noticed that many constraints generated from program are equivalent. So we do caching, normalized constraints, and use caching for it. And this actually saves a lot of time. So I'll show you some. In one case, if you have worked on constraint solving, string constraint solving, there's a Kaluza benchmark, and we got 87 times improvement for that data set using caching. And I'll just show you how good the caching is. So there are, if you know this data set, it's a string constraint data set generated by symbolic execution, okay? It has 1,300 constraints that are big constraints. So they classify the data set to small and big constraints. So the number of constraints that are big are more than 1,000, 1,300. But if you use normalization, actually there are only 34 equivalent constraints. So this is the tree map of those constraints. So there are like 253 constraints are equivalent. There's one of the, we can map that to one constraint. So we can cover all these 1,300 constraints by actually solving 34 constraints, okay? So there is a lot of equivalent constraints. For the 17,000 equivalent, 17,000 small constraints, there are actually 360 equivalent constraints. So you just have to solve 360. So if you do caching, you can only solve once, and you will get, for example, in this case, 2,500 equivalent constraints. So this is very helpful, improves the performance a lot. The other thing we did is more caching. We cache sub-formulas. Automata provide a canonical form for constraints after minimization and determinization. So you can actually do something like BDDs. You do have compute cache. You store the automata, and then if you match later on sub-formulas, you can get the result from previous using the compute cache without doing any more computation. So sub-formula caching leads another, like order of magnitude improvement in attack synthesis, which I'm going to talk about next. So now, before I go to the attack synthesis part, so this was a pretty quick, summary of what we did with ABC. So I'll do a demo, but I'm happy to take questions about this.
This is very, very impressive. Tevfik, I've been knowing you for a long time. I know you've been working on this for, probably 20 years, right? Even
that is true.
Way before side channel was a hot topic. You have been working on, this using automaton to do constraint solving, and then, I mean, even back, in probably in the 90s, you had a paper on, at CAV on, constraint solving related somewhat to Pressburg arithmetic. So I'm so impressed that all of a sudden everything tied up together, and then it's a beautiful story, and it's really, really impressive. Here is a question that is asked. It's related to the compiler. You showed an example where you're showing the Java source code, but I guess Java Pathfinder internally works on the bytecode. So there is a question: is there a guarantee that the compiler may add additional set channels, during the compilation or even the execution, right?
Yeah, that's a very good question. So you are right. Actually, I showed the source code, but it does. Java Pathfinder does work on bytecode. So it's bytecode level analysis. And I tell you, we have recent papers that basically show you that bytecode analysis, if you say it's safe with bytecode, it's not guaranteed to be safe at runtime if just-in-time compilation is enabled. So, and we actually have a paper in Security and Privacy this year, IEEE Security and Privacy Conference and ICSI conference just a couple of weeks ago. We showed that just-in-time compilation does introduce leakage, and it's very bad. So I mean, we don't have an exploit, but basically, under certain assumptions, there is huge leakage everywhere. And it's a very concerning thing. I don't exactly know the implications, but we have Tegan, my student who's graduating this summer. She did this amazing work, and she showed basically there is a lot of leakage due to just-in-time compilation. But this doesn't, so, I mean, you can turn off just-in-time compilation, and that would help. So these are all techniques. Again, if you want have soundness guarantees, you need to have certain assumptions like, there is no runtime change in execution time. So you say, disable JIT, for example, or do the binary level analysis. So you can do at the binary level plus add some noise modeling, you know, so model the noise. I'll get to that hopefully at the end. So yeah, I still have 15 minutes. So I'll mention that a little bit.
So here is another question asked by Subash. I guess he's interested in knowing what's the reason why you're focusing on linear arithmetic and string during the model counting constraint solving. Is it based on the fact that Java bytecode have a lot of those, or is it based on the fact that those constraints are decidable, or like related to completeness or something?
Yeah. So this is a very good question. Nonlinear constraints are hard. That's why. So we cannot do well with nonlinear constraints. That's actually, we would love to do nonlinear constraints. We don't have good techniques for that yet, other than basically just it blows up. But yeah, I mean, nonlinear constraints would be great. For nonlinear constraints, currently we would do approximation. We will over approximate it. And so you would miss leakage, or you would enumerate it. So bit vector model counting would be great. I know there are people who work on this. I mean, model counting, there's a big area. I showed you what we did. Kuldeep, for example, Kuldeep Neal works on, bit level binary model counting. They can do more things. There's other recent work on bit vector model counting. But I tell you, for the size of domains we can handle with linear arithmetic and strings with model counting, there is no other tool that can handle what we can handle. If you look at it bit level, it blows up so fast. So the efficiency we achieve for linear arithmetic and strings, nobody else can achieve at the model counting level. I don't know any tool that comes even close. So
actually, Kuldeep just asked a question. So in your ABC solver, are you converting everything into DFAs, or is like a combination of DFA with something else?
No, we don't convert to DFA. We do not have to convert to DFA. We can do and or. So we can do ands and or. So we don't have to. But so there is, I mean, there are so many heuristics we put there. You know, it's basically we do a combination of things, but we need to get the initially we push the negations down so that can blow up, but it's not necessary. I mean, again, we can do and or, so we don't need to do DNF representation. So we can capture, since we can handle complement. But there are all sorts of, there's all sorts of details there. But I want to do a very short demo on this. So I want to show you ABC running on the example. Oops, actually, that's not what I want to stop. Okay, let me share the other screen. I think it's this one I want to share. So this is, so let me just show you first, okay, before I, oops. So this is ABC. I'm going to run it on a constraint. I'll show you the constraint later, but let's run it. ABC running, basically look, it returned immediately. Bound 0, count 0. So now what did we count? This is the constraint I used as a running example. Variable not in AB star, okay? Remember the numbers were 0. We can go back to the slides. So there was no solution of size 0 length, okay? And I think there were 2 solutions of bound 2. So now this is the bound variable. I'm going to make it 1. So no solutions of size string length 1, 2 solutions for length 2, length 1, sorry. So its count is 2 there. And now I can do how many solutions of size 2, length up to 2. This is actually going to add now, I think it was first 2, then 3. Length 2 was, there were 3 solutions. So, but this is doing up to 2. So it's going to count the number of solutions for length 0, 1, and 2. And it will give us 5 because it's now 2 plus 3. Now, if I do bound 3, it's going to, I think it was, I don't remember now. Maybe it was 8 next. So it should be 13 now if I go to, and it is 13 here. And I don't remember. I think maybe it was 15 next. Actually, I don't remember. We need to look at it. So for length 4, it's going to give, it says 28. So apparently it was 15. So 13 plus 15, it's going to 28. So now you can say, well, what about size 10? And apparently there are 2041 solutions to that constraint. What about size length 100? Well, apparently there are whatever this many solutions here. Okay, so lots of solutions. You can tell here that I'm not enumerating, right? So otherwise, how many solutions are there of strings of length 1000? and that many solutions, right? How many? 10,000, this many solutions. Well, it's hard, so the number is exploding, as you can see, right? But I guess I convinced you that we are not enumerating, but eventually it will slow down. Okay, so it's slowing down now. So there, you know, but it did that too. I don't know what we enter. So a lot of solutions. So, but we can do all sorts of constraints. So let me maybe show you another one. Let me see this one. I don't want to, yeah, so let me show you this. Here is a constraint which basically says string length is odd, but the string is, length is odd, but the string is AA star, okay, AA plus, sorry. So this regular expression is saying, you know, AA plus, the string should be AA plus. This one is saying length should be too odd. Now, if you use this for CVC or Z3, which are very great constraint solvers, they don't return, they basically time out. They can't solve this constraint. So let's solve this with ABC, with also do model counting, not just satisfiability, okay? We'll also model count. But of course, if we are model counting, if it says 0, that means it's unsatisfiable. And it does say very quickly that actually there is no solution, count is 0. And I can, you know, I did that string size 4. I can do, you know, for 10. Is there a solution for 10? But no, apparently there's no solution. So this just shows you, and again, this constraint times out on Z3 and CVC. So it just shows you that Automata has some advantages, you know, that other constraint solvers cannot handle. And also it can do model counting pretty efficiently. So now let me get to the last part. We are going to run out of time. Oops, that's not what I wanted. 1 second. Which is attack synthesis, which is also pretty cool. And I hope I can cover some of that before we run out of time. So attack synthesis is, so here's an example I'll show you. This is from DARPA STACK program. It's called Low Database, okay? This was a challenge problem that was given to us from DARPA when we were working on that program. And it has secret and public IDs in this. It's a law enforcement, it's a police department's database, let's say, right? They have restricted and unrestricted employee IDs, and you can do search and insert queries. And they want to figure out, the question is there a side channel in time that people can figure out the secret employee ID, which should not be returned by search queries. So they give you code, and this is a big code. I mean, it's thousands of lines of code, Java code, and they say, see if there's a side channel, right? And by code inspection, we actually figured out that when you do, you know, search and insert queries, go to this method called channel read, and there's some case switch there, and you know which one is insert, one is search. We did this by using, you know, just inspection, and then we wrote a SPF symbolic pathfinder driver for this, which basically calls this method. And it does a search basically, right? This 8 is case 8, switch case 8 is search. And it does a search within a range. It inserts 2 concrete, you know, public values. It puts a symbolic secret value. This is the symbolic secret value, which is different than the public values, which are 64 and 85. Those are concrete. And then we do symbolic execution on it, okay? Now, once we do symbolic execution on it, now, I showed you something similar. We get these path constraints and we get this entropy, probability, and leakage. So we see some leakage. We see some probabilities. One thing here is, I'll just tell you, constraints could be hard to parse. But what we did is a search between 50 and 100. Okay, so we did a search here. The value 50 and 100 in the search we did, and the search query. Search range is 50 to 100, okay? And when we do this search, we observe that if the secret value, which is H, it's a symbolic variable, if the constraint says it's between 50 and 100, okay? The number of instructions is higher than the case when it is not in the range. So when the secret is in the search range, the number of times instructions it takes is longer. And this is, from these cost and path constraints, you can see this. So basically what happens is if there is a search with it that includes a secret ID, they log this. They don't report it in the main channel, but they do a logging. There was a search, there was a secret within that search range, and they report this, and that increases the number of instructions. So from this, actually, we developed an attack for this code and implemented it. And basically, we do a binary search on the range of IDs. And we implemented this, and we can find the secret. So let's say the secret is between the ranges between 0 and 40 million. We did a search by dividing, we do a query to the first half of the range, second half of the range, and we look at execution times. So if the execution time is higher on the, for example, second part, then we do a query, divide the second part, and do a query there. And we did this for, our attack, and we basically can find the secret and find the vulnerability. So this was something that we did manually at the beginning of this program, but then it came to us, well, can we do this automatically, generate the attack automatically? And it turns out you could. So, and now I'm going to show you a very simple example where there is a secret, there is a public input. And if the secret is less than the public input, let's say the execution takes 1 millisecond. If the secret is greater than the public input, it takes 2 milliseconds. So let's say that's the code, right? So now can you generate an attack? Again, I don't want to do this manually. I want to do this automatically, right? But so I have that the observable is 1 if the secret is less than or equal to public input, and greater than, it's 2 when the secret is greater than the public input. So now you can do queries, if the attacker, for example, gives the value 220, let's say we have a, 1 byte of secret, right? It has 256 values. If the input is 220, then I know that, if the observation execution time is 2 milliseconds, then I know the secret is greater than 220. If it's less than or equal to 220, then it's observable is 1. If I observe 1, and I know that's the case. So attacker's input partitions the domain of S. So as we discussed at the beginning, and I learn information. Now an attacker, how should the attacker choose the input? So if the attacker chooses first 254, then 253, we know that this is not a good attack because we are computer scientists. We know that what you should do in this case is binary search. So you should balance the partitions you get. So this is a very imbalanced partition, and it will do, in the worst case, you will do actually 256 queries to find the secret using this approach. But if you do balanced queries, if you do binary search, you will find the secret actually in 8 steps, right? That's what you want to do. In the worst case, it will take 8 steps. So when this attacker is attacking the, to find the secret, looking at observables, the attacker is partitioning the secret domain, right? And it can get imbalanced partitions, which are not good, or it can get balanced partitions. So a balanced partition is much better because in the worst case, you will do the attack much faster. So that's what we, you try to do, right? So this is, interestingly, balanced partitions corresponds to maximizing the information gain. So, and maximizing information gain leads to binary search. So it turns out, if you maximize the information gain, you get the optimal search. So therefore, and information gain is remodeled with Shannon entropy. So it turns out, if you maximize the information gain, you get the best attacks, right? So we did implement this. This is, automatically generating attacks based on, maximizing the entropy. The cool thing here is that if you maximize the entropy, you get binary search automatically. So you can synthesize the binary search algorithm by the principle of maximizing information gain. But this can be done for any program, not just this simple binary search predicate. You can do any program, you can do the search. So we implemented this. The attacks we generate are adaptive attacks, and we can generate adaptive attacks. So I'm going to skip a bunch, unfortunately. And we do attack synthesis we model the noise, and we can do, offline profiling and generate attacks, pretty efficiently. We use online attack synthesis. Our noise modeling uses profiling. I'm running out of time, so I just want to show you the results. But we do profiling of the noise and take the noise into account. And we actually, get distributions, noise distributions, and using online noise distributions, actually, we generate the attack. So I want to show you one attack example. This is a prefix attack that's automatically generated from using symbolic execution, using entropy, model counting, and everything. And you can see that the secret here is CIQA. And you can see our attack generator first tries, the different characters for the first character, eventually determines that C is the first character and keeps C the same, then gets into second character and determines I is the same. This is all done automatically, eventually gets to the third character and eventually determines the last character, all right? I want to also show you the LawDB example for one more minute. So this is a case of the LawDB example. It's now automatically generated attack, not manually. I'm showing here is the secret is 92. And initially, we don't know the secret. So this is our initial distribution for the secret. We have no information. This is showing you attacker's information about the secret. No information. It's uniformly distributed between 1 and 100. And the secret is at 92, okay? And there are also some inputs at 64 and 85. So it does a search, it does certain queries, and it does update its secret, its observation about the secret. You see the probability distribution being updated by the attacker about what the secret is. And actually it does there is some noise, so it actually gains some wrong information. Currently it thinks it's between 65 and 75 or something, and it's actually wrong, but it does repeated queries and it actually eliminates those wrong assumptions by doing repeated queries. Eventually does another query and realizes that actually there was some noise and its initial guess was wrong, and it slowly converges, not very slowly actually, in 25 steps, it converges to the secret and it eventually finds the secret and reports the secret. So this is kind of scary that you can do this kind of stuff automatically. And I told my students many times, if we really succeeded making this very practical, we may get a call from NSA saying that stop doing research on this. But so far, I would say scalability is an issue, but I think we can scale it better and better. And again, our goal is to not to find attacks. Our goal is to make the software safer, and to go to that step, you first have to find the attack so you can improve the software, right? I mentioned that there is a lot of work on this, so I will share the slides. These are our papers, but there are a lot of papers that I compiled on this. I'll also share the slides. I'll send it to Chao so you can look at the extensive work on this area. But I will just say 3 minutes over time. So I'll just say that I'm looking, if you like these topics, I'm looking for postdoc and PhD students. So please contact, and I'm happy to answer more questions now.
Thank you so much for the tutorial, and it's very interesting. We are doing the recording, so we will probably put the recorded video on the CAV channel later on. There is just one more question that I would like to ask, because this was asked by Ali over the Slack channel. He says, well, this is all cool and interesting. When you finish the analysis, you detect there are some leakage. Is it possible to rewrite the program, or we're doing something to mitigate the leaks?
Yeah, that's a very good question. There is work on mitigation. I know, Chao, you are working on mitigation. We are working on mitigation too, currently looking at, for example, for JIT side channels we detected. So I think mitigation is also important, but I'll say this. To completely mitigate it, you need to go to non-interference, which is not practical. So you need to, for example, make the execution time constant, and that's not going to happen. So there is always going to be some leakage. So this analysis, you can use whatever mitigation you do. After the mitigation, if you want to quantify how much information is still leaking, you would use this analysis, right? So if you are doing your mitigation right, and attack synthesis can also help you with that. We synthesize attacks. As your mitigation gets better, the attack length is going to get longer and longer, right? So, and at some point you are going to say, for example, for the password example, you can say, well, the attack length is, if the attack length is 256, you should not let people have 256 queries, right? So, but if the attack length is 1 million, so then you can say, well, I will allow you 256 repeated queries, and after that I will basically stop the session, right? So this kind of things go together, right? Mitigation, you still need quantitative analysis of how much leaks after mitigation, because non-interference is not practical. In certain contexts. I mean, in some other contexts, it could be practical. Right?
Thank you so much for giving this tutorial. I would like to thank you on behalf of all the audience.
Thanks for the invitation. Thanks, Chao.
Thank you.